Hello everybody, and welcome to exercise 1 at the top of page 66 in the workbook. This is going to be our first example of actually calculating a triple integral. So here they're giving us a solid region in three-dimensional space. It's described as the region below a plane and above a square whose coordinates are shown here. And in part A, they'd like us to find the mass of this region given its density. Okay, now they don't give us units in this problem, but I'd like to make up some units just to help us talk through this. So let's assume that our density is in grams per cubic centimeter. Okay, that kind of means we're assuming that distances are being measured in centimeters as well. Okay, so to do part A here, we might start with the observation that mass we can get by taking the triple integral of our density over our region. And the reason for that is really just units. Okay, rho of x, y, and z, we kind of assign the units grams per centimeter cubed to. And if distances are all measured in centimeters, then a little bit of volume is going to be centimeters cubed. And we can see that if we cancel the units, we're going to get units of grams. Okay, so that tells us that we're on the right track here. Okay, now the hard part when you're doing a triple integral is finding the limits of integration. Okay, so to do that, we're going to need to draw some pictures. And so I'm going to leave a little bit of space for the pictures that we're going to draw. And down below, kind of rewrite the integral that we're looking for. Okay, so doing a triple integral is about integrating in three different directions. Okay, it's kind of up to us to choose which variable we integrate with respect to first. So I'm going to start by first writing in the function that we're given for the density. That's 48y. And let's just choose to integrate in the dz, dy, dx order, just as a choice. Okay, so what that means then is that the first set of limits of integration that we need on the inside would be z values. Okay, and you might remember back from double integrals that the inner integral went from curves to curves. With a triple integral, our dimension is one higher, and so our z limits are actually going to go from surface to surface. We're going to think of it as going from the surface at the lower side of our region to the surface at the upper side. Okay, well, we need a picture in order to figure out what those surfaces are going to be. Okay, so let's first draw in an x, y, and a z axis here. And I'd like to see if we can picture the plane that we're talking about. Okay, x plus y plus z equals 1. We're going to use a strategy of finding the intercepts for that. Okay, so imagine that we take y and z and set them equal to 0. What would x have to be to make this a true statement? Well, it would have to be 1 because 1 plus 0 is 1. And so one point on this plane would be 1, 0, 0. You can play that same game with the other variables. If you take x and z and make them 0, y would have to be 1, which gives us the point 0, 1, 0. And play the same game with z. There's a third point. And so if we play connect the dots here, that plane, x plus y plus z equals 1, looks like that. Okay, if we just graph this small part of it. Okay, and the other part, okay, that was the surface that was on the top. The surface on the bottom was this rectangular region that they're describing. If we draw that into our picture, it would look like this. So there's x equals a half and y equals a half. Okay, and if we look at all x values between x and y values between 0 and a half, we're going to get a little rectangle that looks like that. Okay, so back to the idea of the limits of integration. Okay, these two numbers here and here. We want to ask ourselves, as we look at this solid, what is the surface that's on the bottom of the region? And as we kind of move up, we smack into the top surface. What's the surface on the top? Well, we can see from the picture that z is equal to 0 on the bottom. That's a flat plane at the bottom. And what's z equal to at the top? Okay, well, remember that the top of our region is formed by this equation up here. So all we really have to do to figure that out is to take that formula and to solve it for z. Okay, we can do that by just subtracting the x and the y from both sides. It tells us that another way of writing that formula is z equals 1 minus x minus y. Okay, so in a nutshell, z equals 0 is our bottom surface, z equals 1 minus x minus y is our top surface, and so those have to be our limits. Okay, so from z equals 0 to z equals 1 minus x minus y. Okay, and then we move on and ask, what are our y and our x limits? Okay, well, oh, and actually, just to maybe keep a little bit better track of what we're doing here, I'm going to also write out in words the limits that we got. So our lower surface was z equals 0. Okay, and our upper surface is z equals 1 minus x minus y. This is just kind of for the sake of your notes when you're looking back at this. Okay, so we're done with the z direction, and so we're going to do what we did in the previous section. We're going to shine a light down the z-axis and ask, what would the shadow look like in the xy plane? Well, our shadow is just going to be this region R that we have, which I'm going to draw a second picture of over to the right here. Okay, R is just a square region. Okay, and we know what its size is. And so now we're ready for the y limits of integration. And so we're going to ask ourselves, if we integrate top to bottom in this picture, what's the curve on the top and the curve on the bottom? Well, both of those are horizontal lines, and we can see that they're 1/2 and 0. Okay, so those have to be our y limits of integration. Okay, and now we are done with the y direction, so we're going to shine a light down the y-axis and ask, what's the shadow if we do that? Okay, the shadow is going to be on the x-axis, and it's just going to take us from 0 to 1/2 again. Okay, so we've figured out what our three limits of integration are, and we're ready to actually calculate the integral now. Okay, and the process here is the same as what it was in the last section. We've just got an extra dimension going on. Okay, so I'm going to start by just rewriting the two outer integrals. And now what we need to integrate is 48y with respect to z. So remember that y is being treated as a constant. We take an antiderivative of 48y with respect to z. We're just going to get 48yz evaluated between our limits, which look like 1 minus x minus y and 0. Okay, so fill in our limits. And let's see, upper limit is 1 minus x minus y, so that's going to replace the z. And notice that the lower z limit is 0. When we plug that in, we're just going to get 0. So I'll put a minus 0 there, and we've still got the dy and the dx to go. Okay, so let's rewrite that. Okay, if we take that 48y and distribute it through, we're going to get 48y minus 48xy minus 48y squared dy dx. Okay, and we've broken it down to a double integral. And double integrals are what we did in the last section, so this process is going to seem familiar, hopefully. So now we need to integrate our function with respect to y, so we'll be treating every x as a constant. So let's see if we do that. Integral of 48y is going to be 24y squared. Okay, next term is going to turn into 24xy squared. And then finally, 16y cubed for the last term. Okay, we're evaluating between y equals 1/2 and y equals 0. dx. Okay, and so now we're going to plug in 1/2 for all of our y's. So let's see, we would get 24 times 1/2 squared minus 24x times another 1/2 squared minus a 16 times a 1/2 cubed. Okay, there's our upper limit, and our lower limit, we'd just be plugging in 0 for all of our y's, so that's again going to be 0. Okay, and without going through all of the algebra here, I'm just going to show you what this looks like if you simplify all of it. This is going to collapse down nicely to just 6 minus 6x minus 2. Okay, and once we get to this point in the problem, I'm going to assume that you could do this calculus 1 integral. Okay, there'd be a little bit more work, but what we would end up with is 5/4, and we already noticed above that the units are going to be grams of this. Okay, grams per centimeter cubed times centimeters cubed. Okay, and so there is the mass of the region that we're talking about. Okay, and I believe that that is part A. Okay, that was a lot of work. We had to do a lot there. You can see there's a lot involved in doing a triple integral. Let's talk about part B though. Okay, so now they'd like us to set up but do not evaluate an integral that gives the volume of the same region E that we were talking about. Okay, well, what would be different about finding the volume? Turns out that all that's really different here are the units. Okay, and I claim we can find the volume of this region by simply integrating over E and simply integrating dV. Why does that work? Okay, well, think about what dV is. It's just a small, tiny cube of volume in this region. Okay, so it has units of centimeters cubed. That's already a unit of volume. Those are the units that we want. So you can kind of picture this integral as being kind of going over the entire region E and just adding up volumes of little cubes until you're done. You're going to get the volume of the whole region. Okay, so in a nutshell, there's not a whole lot to do here because we already know what the limits of integration are. They're going to be the same as they were in part A. Okay, the only difference is that we're integrating dV. Okay, there's kind of an imaginary 1 in front of here. We're integrating the function 1 dz dy dx. Just so we can maybe tell our answers apart. This is going to be our answer to B. Okay, so they didn't ask us to evaluate this integral, but if we did, it would give us the volume of the region E.